Hi everybody, welcome back. We are continuing our series of videos on regression. In the last video I introduced the very basics of regression, what a simple linear regression equation looks like with one variable, and then we added a series of variables to get multivariate regression. And we have a fairly generic equation here. We could add more variables than just, we have x1 as the first independent variable, x2, x3. We could have several, we could have dozens, we could have theoretically hundreds of variables on that right-hand side of our equation. But using our health insurance example from the previous chapter, as an example here, we can see that if we're interested in looking at the effect of health insurance on health, we can see that we have our primary independent variable of interest, which is health insurance, and then all of these other variables, here we would have a bunch more, to help control for other factors that might impact a person's health other than health insurance. And the reason why we include all of those variables is, remember that these betas are the effects of the variable on the outcome, so the effect of x on y, and the kind of nuanced details behind that effect are what really matter here. So recall, our interpretation of beta is the following. And in this particular case, we're going to do the interpretation of beta 1. Okay, this is the impact of a 1 unit increase in x1 the impact of, or relationship, of a 1 unit increase of x1, in our example, health insurance, on yi. So in our example, health. So the effect of a 1 unit increase of health insurance on health. And then the key part here is that we're holding all other variables constant. Okay, and in the example above, we have age, and we have hours exercised. But this could also include things like gender, income, race, other health habits, diet, and so on and so forth. And so what we're doing is essentially we're holding all of these things constant so that when we're making a comparison, everything is equal except for whether or not somebody has health insurance. And so that's if we control for enough other effects, this beta 1 is only the effect of health insurance on health. If we don't include some of the other variables that we need to, we're going to see that beta 1 picks up some of the effects of other variables when it shouldn't. And that's why if you don't control for those other variables, then they're going to get captured inside of this beta 1 term. So it's very important to try to control for as many possible variables as you can that might also affect the outcome. So beta 1, the 1 unit increase of x on y, holding all other variables constant. One more example of this. Here we have health insurance, which we could really just think of as a 1 or a 0. Either you have it or you don't. But let's take something like income as another example here. The income of person I is going to be equal to beta 0 plus beta 1 times the years of education of person I, plus a bunch of control variables, plus the error term. And so the interpretation of beta here is, okay, if you increase education, or let's say the effect of 1 more year of education on income, holding all else constant. Okay, and so here this could be more of a continuous variable instead of a discrete 1, 0 as we would have in health insurance. This could be like going from 11 years of education to 12, or from 15 years of education to 16, right? And so this beta 1 in this case goes along with a continuous variable, and so it could be a discrete or a continuous, and then that's also part of the kind of design of the regression equation. Is you have to think about how you're going to be measuring these things, and how these variables are coded, right? It could just be, instead of years of education, it could just be a college degree of individual I. That could be a 1, 0. Do you have a college degree or not? And what's the effect of having a college degree on your income? Or it could be how many years of education do you have, call it, say, 1 through 16 or whatever. That's more of a continuous variable, and each of those have a little bit different nuance in how you're interpreting that beta 1. Okay? All right, so now that we have that, let's keep going with these same ideas. And ultimately, we have to estimate these equations in our regression software. So estimated regression equation. Right. So let's suppose that we do have some true model that looks just as we described above. We're going to go back to our simple linear equation with just one variable, beta 0 plus beta 1 x1 I. And this one, we don't need to put the 1 because there's only one variable, plus some random error. So if this was health insurance, beta 1 would be the true effect of health insurance on health. And everything else would be captured in the error term. Okay, but the problem is we can't actually observe the true effects. Especially absent a randomized control trial. So we can't actually observe the true effects, meaning beta 0 and beta 1. So we have to estimate them. So we have to estimate them empirically the best we can. All right, and when we do that, we're going to call beta 0 and beta 1 hat. We call that beta hat, beta 0 hat, beta 1 hat. And the beta hats are the estimates of beta 0 and beta 1. Okay, so we don't know the true effect of health insurance on health, or we don't know the true effect of years of education on income. But we can try to find as close an estimate as we possibly can. And when we do that, we're going to estimate the following equation. yi hat, anytime there's a hat, it means estimation. So yi hat is equal to beta 0 hat plus beta 1 hat times x I. Okay, what's different here? One, the y now has a hat. X does not. X we can measure. And where's the error term? So what about the error term? So that's missing. And then also we have yi hat is the estimated value of yi. Okay, now yi, this is actually observable. And so what we're essentially trying to do is estimate a beta 0 and a beta 1 such that we get a close estimate of the outcome, as close as true to possible. And what are we defining as close and what's as close as possible? That's what we're going to discuss here. So we want to observe, or we want to estimate a beta 0 and a beta 1 such that yi hat is close to the true value yi. So we want to estimate beta 0 and beta 1. So if we're looking at the effect of health insurance on health, then when we put these into the regression equation, we're going to have a very good estimate. To do that, we need to talk about the residual, which is not epsilon, but just E. This is something that we can observe. Okay, the residual denoted EI is the difference between the true yi and the estimated yi hat. Is the difference between the true yi and the estimated yi hat. Okay, and so there's a simple formula for that. It's just yi minus yi hat. That's our residual formula. And that ultimately is going to lead to the following regression equation. So we have, okay, this leads to the following regression equation. So if we start out with our estimated yi hat is equal to beta 0 hat plus beta 1 hat xi. And if we also know that ei is equal to yi minus yi hat, we can rearrange this a little bit so that we have yi hat is equal to yi minus ei, and then plug that back in to the original. So we're going to plug this into here so that we have yi minus ei is equal to beta 0 hat plus beta 1 hat xi. And then finally, from that, we're just going to move the residual over to the other side so that we have yi hat is equal to beta 0 hat plus beta 1 hat xi plus ei. Okay, and so ultimately we can compare that to where we started this entire chapter, where we had the true yi is equal to the true constant regression coefficient plus the true regression coefficient on xi plus epsilon I. So this is the estimated model, and this is the true model. And so this is when we replace the theoretical or what we can think of as the true coefficients beta 0 and beta 1 with the estimated coefficients beta 0 hat and beta 1 hat. So when we replace the theoretical coefficients beta 0 and beta 1 with the estimated coefficients beta 0 hat and beta 1 hat, then the error term epsilon I must be replaced by the residual. Must be replaced by the residual EI. We can really kind of think about EI as almost as epsilon I hat, if you want to think about it that way. Okay, so we cannot observe the true error term. We cannot observe the true error term, but we can observe the residual. EI when we estimate a regression. Okay, and so I'm going to leave it here for this video, but I'm going to continue along with the same line. And what we're going to be doing in the next video is looking at, with just a one variable example, how regression looks like graphically, and to give you a better idea about what we're talking about when we're talking about these residuals, and how a regression is actually functioning in practice. Okay, so we're going to look at that in the next video. Thanks for following along, and I'll see you there.